So today we have an explainer from Cornell, and he will tell us about some very exciting sequence of works, constructing zero-knowledge PCPs, and
Great. Yeah, it's great to be here at IS. See some familiar faces. Yeah, I'm going to be talking about sort of a couple of recent works, which are joint with Tom Gurr and Jack, who is here in the audience, who are both at the University of Cambridge. I guess most people in this room know what a PCP is, but I'm been told not to assume that. So I'm gonna, introduce PCPs in like a PCPs and zero-knowledge PCPs in a friendly sort of way. So hopefully everyone has seen the graph 3 coloring problem before, right? So you want to give like some coloring of a graph with 3 colors where each adjacent pair of vertices has a different color. This is the Peterson graph, and so it's well known to be 3 colorable. Here is a coloring that I got from Wikipedia. So the goal here is going to be to like prove to somebody that this graph is 3 colorable. Okay, so that's kind of the whole name of the game is like to convince a verifier, like an efficient party, that this graph is 3 colorable. And we're going to do it in a kind of strange way. Obviously, there is a way. Like one way is to do what I said, which is what I'm doing here, which is just show you the 3 coloring. But we're going to want to do it in a way that's kind of has some interesting properties. This method was suggested by Algebraic, Macaulay, and Abbey in 1986. And the idea is, first, what we do is we permute the colors. Okay, so I'm going to choose a random permutation of these 3 colors, red, green, and blue, and I'm going to recolor take my coloring and just recolor it with this permutation of the color. And then I hide all of the vertices under hats. And I allow you, as the verifier, to choose some edge and remove both the hats from the endpoints of that edge, right? So like that. Okay, and then you as the verifier, you're going to be convinced if the endpoints of that edge have distinct colors. Okay, so why did we do it like this? Well, this sort of method of proving this to you has a couple of nice properties. The first one is that it has some sort of like probabilistic checking property. So you don't need to look at the entire graph to be convinced to some extent of the 3 colorability, right? You are kind of looking at this local check. You're kind of making 2 queries, right? You're looking at 2 vertices. And it's fairly easy to see that if this is not a 3 colorable graph, then there's going to be, in any coloring, there's going to be one edge that is not properly colored. And so the probability that you accept in no instance is bounded away from 1, right? It's like at most 1 minus 1 over the number of edges. Okay, so I'm going to call this like a weak probabilistic checking guarantee because, you get some guarantee, but like it's kind of, this is not what you would hope for, right? It's something that kind of approaches 1 as the graph gets bigger. The second property that we have is some sort of weak zero knowledge. So what do I mean by zero knowledge? Well, let me say first like why this graph has zero knowledge, and then I'll say what zero knowledge is. So notice that the distribution, the marginal distribution on any single edge, on the endpoints of any single edge, is very simple, right? It's just going to be uniformly distributed over sort of pairs of colors that are distinct, right? And like if I randomly, permute the colors, then it's not too difficult to show that this is going to be the distribution of the kind of marginal single edge. Okay, so what zero knowledge means is basically that like the distribution should be in some sense independent of the actual coloring that you that you're getting. Okay, so I'm going to make that formula in a couple of slides, but that's what you should have in mind. Okay, so it has these nice properties, but unfortunately they're quite weak. In particular, the zero knowledge property is very fragile, right? Because if I allow the verifier, if I'm not quick and they are able to remove 1 more hat, then they see that these 2 vertices are colored the same, and this is not something that I is going to be invariant under the choice of coloring, right? Like it might be that now I've revealed that the coloring that I have has these two vertices colored the same, and no matter what permutation I put on the colors, this is going to always be true. So now I've revealed information about the coloring, which is something I don't want.
It's not clear if it's weakness of the zero knowledge property or weakness of the encryption function you use for your heads.
Yeah, I guess if I guess it's like weakness of me in like not preventing you from taking more of my hats, right? But let's say that I'm not quick enough to prevent you from doing that.
You're not making explicit the cryptographic.
Yeah, I'm not going to talk about any cryptography in this talk. Yeah. Good. So the idea of zero knowledge PCPs is basically to like strengthen both of these properties in this setting. So now let me sort of formally define what I mean by PCPs and zero knowledge PCPs. So in a PCP system, you have some verifier, so a probabilistic polynomial time algorithm that is trying to determine whether an instance X is in the language poly. And the way that it does it is it's presented with this like very long proof string, and it's going to make some number of queries into that proof string. So it's going to choose some positions, right, some of these hats, and it's going to lift up some of the hats. And we want some basic properties. So we want completeness. Like if X is in the language, then there is some proof string I can write down that will make the verifier always accept, right? 3 coloring in this case. And then we want sort of a stronger soundness property than we got in the 3 coloring case, which is that if X is not in the language, then no matter what proof I write down, the probability that you reject is always at least half. Okay, so you have a pretty good chance of rejecting false proofs. The important parameters for this talk are going to be the length of the proof, okay, which I'm going to basically insist is polynomial for most of this talk. And the query complexity of the verifier, so the number of positions that the verifier looks at. And for this to be interesting, we really want this query complexity to be much less than L, right? If you can read the whole thing, then this is just like you can use the NP limit. So the most important result about PCPs, arguably, is the PCP theorem, which says that NP has PCPs with polynomial length and constant query complexity. Okay, so you have a PCP for any language in NP where this L, like the length of this proof, is polynomial, and the verifier need only look at a constant number of positions in order to like reject with this very high probability. Okay. Great. So that's PCPs. Any questions about that? Okay. Great. So what is zero knowledge in the concept of PCP? So this is like maybe something that you haven't seen before. It was defined originally by Killian, Petranka, and Todesh in 1997. So in as a like zero knowledge experiment for PCPs, we have some machine V star, which is an efficient machine, but otherwise we don't constrain it. This is like the adversary. And the adversary is going to make some queries to the proof. Okay, and it's maybe different queries to the honest verifier. It may be many more queries, right? It's going to make some number of queries to the proof. And what we want is that we can simulate the sort of view that the verifier has using a probabilistic polynomial time simulator that doesn't have access to the witness for the for the membership in the language, right? So it's like S in particular doesn't really know whether the instance is in the language or not. So the sort of leverage that the simulator has over the original proof string is that the original proof string is kind of fixed prior to the queries, right? You have to write down the whole proof string and then you get to make the queries. Whereas the simulator is able to answer adaptively, right? So it can kind of receive one query at a time from this verifier and like make up its answers on the fly as it goes along. So the important parameter here is what we call the query bound. So this is kind of the restriction that we're going to place on this V star, which is that the number of queries that V star is allowed to make, it can make arbitrary queries, but it can't make more than this number Q star. Okay, And kind of the reason we have to do that is because it's not too difficult to show that if we can just query the entire proof, right? If V star is allowed to query everything, then this is just trivial, right? So like you only get BPP. Like the simulator can essentially like be used to decide the language in this case. But we would like this Q star is a lot more than kind of the honest query complexity of the verifier, right? So this Q is the query complexity of the honest verifier. We would like that kind of, even if you make a lot more queries than the honest verifier does, then you still have some kind of zero knowledge notion. And similarly to kind of more standard notions of zero knowledge, you can define perfect statistical computational zero knowledge. I'm not going to go into it. Basically, it's to do with the quality of the simulation, like how distinguishable are these real and ideal worlds. In this construction, we get perfect zero knowledge, so these are identically distributed. So I'm not going to worry about weaker. Any questions about the definition?
For those who never saw this, is the ability to simulate means zero knowledge. You can, you didn't learn anything if someone who doesn't have access to the proof can generate the same conversation.
Right. Yeah. So like the way that we kind of formally capture the idea of not learning something is to say that, you could have learned it even without interacting with the proof, right? You could, any information that you can learn up here, you could have like sat at home and run the simulator and you would have learned the same information.
This has to hold only for X's in the language.
Yes.
We don't care
about X's not in the language, right? No one is going to try and generate such a proof. Okay. Any questions? Cool. All right. So what do we know about zero knowledge PCPs for NP? So the original work, KPT, gave a quite nice construction. So polynomial proof length, the query complexity of the honest verifier is polylogarithmic, so pretty small. The query bound is exponentially larger than the query complexity, which is also nice. They achieve a statistical zero knowledge.
What's the language?
Of NP, all of NP.
The polynomial is polynomial in Q or polynomial in D
good, yeah. So basically I can set, so what I mean here is that I can set Q star to be any polynomial that I want. And all that will happen is that this proof length will go up. But that's it.
Well, normally in the original witness length.
Yeah, exactly.
No, polynomial it means n to the epsilon.
Yeah, or some n to the, or like n to the anything, right? Like
Where n is?
N is the length of X, so
N
N
is
will
the length of the
be
original witness.
N will be n to the 10, and Q star will be n to the 1 over 10.
It can be even so. What they get actually, and what we will also get. So you can basically set Q star to be what you want, and the proof length will like grow with Q star.
It'll be some big polynomial in Q.
It'll be exactly like Q star to the 10 or something. That's
and bigger than X.
Yes, exactly. Good. Okay. So the kind of one of the big downsides of this is this asterisk. So this scheme has an adaptive honest verifier, which is very unusual for PCP constructions. So what that means is that, you lift up a hat, and then depending on what's under the hat, you choose what hat you're going to lift up next, right? Whereas with most PCP constructions, you can kind of decide in advance, I'm going to lift up hat 10, 12, 15, right? And just lift them all up at the same time.
Can you say in 2 sentences a hint of how this construction works?
Yeah, I mean, it's like quite complicated, so I don't understand it entirely, but the idea is that, so you have a construction that works so long as the verifier makes queries that are distributed like as the honest verifier's queries. And then you use some sort of it's called a locking scheme. It's like some sort of information theoretic cryptography to enforce that unless the verifier makes queries that are like distributed in this way, they don't learn anything. So yeah, to be honest, I don't understand it very well. It's like quite a complicated construction,
You have a better result, which you do understand.
which I do understand. Yes. So.
Can you explain again the adaptive honest verifier? I don't understand why what you said is a disadvantage. It seems like you allow more power.
Good. So in all of these cases, the malicious verifier will always be allowed to be adaptive, right? So the adversary can always be adaptive, but this is about the honest verifier, right? So the honest verification procedure needs to be adaptive here, right? Whereas we would like to have an honest verification procedure that's not adaptive. And actually that's going to be important. Like this is kind of the reason why they can't go from polylog to constant in the query complexity, because it's adaptivity. Okay. This adaptive honest verifier thing annoyed some people, and so there were a couple of constructions after this that tried to get rid of it. So the first one, this is Ishai, Weiss, and Yang, I think. So they get rid of this adaptive honest verification problem, but at the cost of having a much worse zero knowledge guarantee. So they achieve something called witness indistinguishability, which means that like it kind of only makes sense for languages with witnesses like NP, that the choice of witness does not affect the distribution of the proof string, which is kind of like it is a much weaker version of zero knowledge. In particular, it kind of corresponds to the simulator being unbounded, and if you take a language in UP, right, with unique witnesses, then this is meaningless. Like it's sort of trivially witness indistinguishable because there's only one witness. Okay, and then more recently, this is Kamikaze and Mutu and Weiss. So they recover this like statistical zero knowledge, but they take a big hit in terms of the query parameters. So they no longer have like polylog query complexity. They have some like end of the C query complexity for some C greater than 0. And the gap between the query complexity and the query bound like is only kind of a multiplicative square root. So this is the state of things before we did this one. Any questions about that?
I have a very naive question. It seems that from your table, HVW22 is kind of worse than KPT 97.
But they don't have this adaptive honest verifier.
Ah, okay,
Yeah. So that was what they were trying to get rid of. Good. Okay, so what do we show? So we show that for any Q star, which is going to be this query bound function, NP has PCPs with the following properties: perfect zero knowledge against Q star bounded adversaries, proof length, which is polynomial in N and Q star, query complexity, which is constant, and also a non-adaptive verifier. Okay. So a note about Q star. So I didn't say it here, but Q star should be, almost exponential. Otherwise, the proof length will be too big to actually index into. But if I set Q star to be exponential, then actually this sort of, I get an exponentially long proof, but what I get for that is I don't need to have a query bound anymore because I assume my adversary is polynomial time, and so it can't possibly make more than polynomial many queries. So I also get this like range of parameters if I want. Okay, so let me put that in the table. I've colored the table so that we get all green stuff. We get constant query complexity, polynomial query bound, and perfect zero knowledge. And we don't have this red edge. Okay, so that's just the results I'm going to present. Do you have any questions about the statement of the result before I go on? Yeah.
Is the last three all start with any general PCP and you do zero knowledge afterwards, or that's not how?
So these three all operate like that.
Oh.
What we do is we actually like build a PCP that like specifically is kind of zero knowledge friendly. Yeah, it's an open question whether you can like get this by kind of starting from any PCP and doing some transformation. Good. Okay, so what do? Basically, we follow like the classical PCP recipe. Okay, so, teleport back to the early 90s. So we start with some arithmetization of NP. So like a reduction from an NP complete, any NP complete problem to sort of an algebraic problem that is kind of captures that. And then we put on top of that a protocol for solving that problem. So this is called the sumcheck protocol in the literature. It is a PCP for this like specific polynomial summation problem that I'll talk about. We need to add to that something called a low degree test, which basically ensures that this arithmetization, kind of the witness that we give, has the correct form. And if we like stick all of those things together, then we get a PCP for NP with polylogarithmic query complexity, assuming that you have like a good enough low degree test. So that's good, but it doesn't get us all the way. So if you want to go to order 1 query PCPs, then kind of the modern perspective on this. So what you need to show is that basically this PCP that we constructed before actually has a stronger soundness property, which is called robust soundness. I won't go into what that is, but this robust soundness allows you to employ this technique called proof composition, where you like take your robust PCP for NP with polynomial query complexity, you compose it with a PCP for circuit sat with constant query complexity that has some other parameters that are not as good. And you kind of get the best of both worlds, and you get a PCP for NP with constant query complexity. So this is like the one slide, how you get the PCP there. Okay, so for zero knowledge PCPs, we just do exactly the same thing, but we like throw in zero knowledge in places where we need zero knowledge. Okay, so I should say, so like this is where the adaptivity comes up, right? So like in order to use this, in order to like even talk about robustness, you really need the PCP to be non-adaptive. Like I don't think there is a definition that makes sense for robustness for adaptive queries. Good. Okay, so recipe for zero knowledge PCPs is the same thing, except that like I've thrown in these letters ZK and the places in some of these places. Okay. So we design a zero knowledge PCP for this sumcheck problem. We design a zero knowledge friendly arithmetization of NP that kind of fits well with this to get zero knowledge. The low degree test can stay the same. We don't need to change that. And that gives us a robust zero knowledge PCP for NP with this polynomial query complexity. And then actually we don't need this PCP to be zero knowledge, basically because it only operates on very small parts of the proof. So it kind of doesn't matter very much. And once we do that, then we get a zero knowledge PCP for NP with constant query complexity. So a lot of the work in this picture, I mean, like besides the blocks, is to show that this proof composition thing is kind of preserves zero knowledge. So you need to show that if you start with a zero knowledge PCP for a robust zero knowledge PCP for NP, and you like compose it and you do a bunch of other transformations to it, then this zero knowledge is kind of maintained. So that's something that we do. Yeah, so this thing can be, it does not need to be zero knowledge. We just use an off-the-shelf construction. Okay, so I'm going to focus on this pink box for this talk. The other stuff is also very interesting, but I don't have time to talk about it. And I think this is kind of, yeah, like this object is kind of what gets you there. Like once you have this, then everything else is, mostly turning the wheels. Yeah. Okay, so what is a PCPP for polynomial summation? Okay, so you are given, you're kind of assuming that you're in a world where you have access to this m-variate low-degree polynomial over a finite field F. Okay, and you're allowed to like evaluate it on points of your choosing. Okay, so you're not, this is a huge object. You're kind of not given. Sorry, it's a large object. You're not given like direct access to the coefficients of it. You're given like access to kind of single evaluations of this thing. And what you want to decide is whether this polynomial, if I take its sum over this set H to the M, where H is some like subset of the field, right? Think about this as being some polylog size subset of the field. Then this is equal to M. That's what I want that's what I want to have demonstrated to me. And the way that we do this is by like providing a PCP. Okay, so we provide this like proof string, and by making some queries to this oracle and also to the proof string, you should be convinced one way or the other that P of X is equal to that, the sum of P of X is that. So this is like a really key subroutine in a lot of PCP constructions, and we're going to try and sort of zero knowledgeify it. Any questions about this problem? All right. So that's the sort of PCP definition of the PCPP. What about zero knowledge? So it's quite similar to the zero knowledge definition for just PCPs, but we have this kind of extra complication of having this oracle here, right? This P oracle. And so in the ideal world, the simulator will still be PPT, but it also has access to sort of the same kind of access to this P oracle, so it can make queries. It doesn't have access to the description, but it can like query into the P oracle. And the guarantees, so we need that S is PPT like before, but we have this like extra guarantee that we need, which is this kind of like S makes like a bounded number of queries to P, right? So there should be some polynomial, which is kind of the query blow up, such that if the V star makes Q star queries to everything, like both the proof and P, then S should make this like gamma of Q star queries to just P. Okay. And we would like this kind of blow up to be as small as possible. So that's the definition we should do. All right. So we will need this in the sort of multivariate setting, so where we have like polylog n variables, but it's much easier to explain it in the bivariate setting, so I'm going to talk about that. Okay, so we have this polynomial p, which is bivariate, and I want to, like what I want to establish is that the sum over this blue square up here is equal to n.
Okay. That's because whether the verifier has polynomial time is hard. I mean, you want to stress that there is no time to read all the k-squared entries in P.
So, I mean, I guess he can, but he doesn't have enough queries, right? Like
That's what I'm saying.
yeah, exactly. Yeah. So he's like, yeah. So
Q star is much less than
Q star should be much less than, yeah, exactly. Yeah. So in this setting, like in this sort of simpler setting, I'm going to allow the verifier to make like order of k queries to P and to the proof. Okay. So, you know, in the end, we're going to want this to be like polylog, but here I'm just going to say like you can, you know, you're allowed to make kind of order of k, but not order of k squared, which is what you would need to actually evaluate the sum. And the zero knowledge properties that we're going to go for is that I want to simulate Q star queries to P and the proof with like order of Q star queries to P. Okay, so again, you know, this is going to be non-trivial because like I'm not allowing this like quadratic law. So there is like a standard way to do this if you don't worry about zero knowledge, which is to write down these like partial sums, right? So for every alpha in the field, I'm going to like fix alpha and then sum over B, right, the second coordinate, and I'm going to write down what that sum is. And so there's like one for every row in this table, so I get this kind of column which contains all of the sums. So it's not too hard to see, I think, that this, sorry, this is how you check it, right? So the way that you check it is first that you check that sort of like this part of the sums is going to actually sum up to n, right? Which it should if it's correct, if the proof is correct, then, you know, this is just like summing over the a's. And then I need to check that the proof is actually kind of consistent with the original polynomial. And so I choose a random point here and I check like this polynomial equation on this point, which requires querying like this chunk. Okay, so the overall query complexity is roughly like order K. Okay, unfortunately, this is not zero knowledge, right? Because if I have a verifier that makes a single query to the to this proof, right, then that requires you to like look at K positions here in order to figure out what that should be. And indeed, you shouldn't expect it to be zero knowledge because this was a completely deterministic construction, right? And kind of zero knowledge requires some randomness. Is it clear why this is not zero knowledge according to my definition of zero knowledge? Okay, good. So we're going to try and fix this. So there is an idea.
It was not clear to me why
It wasn't
it's not zero knowledge. You are still, the simulator still has K queries, of K queries.
The simulator, so what I want is that if the malicious verifier makes Q star queries, then the simulator should make O of Q star queries, right? So
Sorry,
yeah.
that's just one.
Yeah, so if I just make one query, right, then I shouldn't need to do K work in order to
So
simulate it.
it's not about the knowledge, it's about the number of queries.
Yes, exactly, yeah.
Why is that the property that you want from the
Well,
simulator?
in generally, we want a polynomial bound on Q star. That's just a
Right, so-
demonstration.
So yeah, the idea is we're going to basically show, like, the way that this will work is we'll like compose this with something else that shows that like a small number of queries to P doesn't leak any information, right? But then you need to make sure that like by adding this proof, you don't kind of leak a large number of queries to P, right? So like this P will be chosen such that it's okay to make a small number of queries, but not to make a large number of queries.
I guess the dimension goes higher, you will lose this, I mean, this constant will become a polynomial number.
Yeah. But the gap will be bigger.
I'm not sure, but, I mean, later we want zero knowledge against a polynomial number.
Yes.
And this is gonna be polylog, so.
Yeah, so what we're gonna do is we're going to like, so we're gonna have a multivariate version of this, right? So P will be kind of much bigger in some sense. And what we're gonna show is that more or less, like if you make a single query to the sort of this part of the proof, then that corresponds to a very small number of queries to the polynomial itself, like the sort of underlying polynomial that you're trying to prove the sum of. And then what we show is that like you can kind of construct this polynomial in a way that it's going to be chosen at random from some set, and you can sort of choose it in a way that it doesn't reveal any information about the witness, so long as you make not too many queries to it.
I understand.
Yeah.
But the question is, so in the end, you're showing us that as long as Q star is some K or something.
Yeah.
The zero knowledge property holds.
Right.
Later, the main theorem says that Q star can be much higher.
Yeah, so K is going to, in the end, it's going to need to grow with Q star.
But it does get to be polynomial.
Yeah.
Okay.
Yeah. So I guess, or rather, it's going to be so here is maybe a little bit deceiving because like the actual number that we care about is like K to the number of variables, right? So here it's K squared, right? And so Q star is going to be something like K to the number of variables. Like that's what we're going to be able to handle.
Okay. It's not clear to me at this point.
From this, yeah, maybe I have some slides on the sort of multivariate case later on, so maybe that'll help. Okay, so just thinking about the bivariate case, so yeah, this is only going to give us like a square root gap between the honest and kind of adversary query complexities, but still interesting. Okay, so how do we get rid of this this thing? So we're going to use an idea from a paper of mine with Eli Ben-Sasson, Alexander Kieser, Michael Fold, Errol Gabazon, and Michael Ryablev, where we kind of add, like we're going to like shift this polynomial by a random polynomial. Okay, so we're going to like in the proof, in addition to this sum, we're going to write down like this whole random bivariate. And it should have kind of the same degree as P, and have the property that it sums to 0 over the pink square. Okay, So the way that we check this is the same as before, right? We're gonna sort of check the sum on the proof, and then we're gonna check the consistency of the proof with both P and R. So for completeness is fine, right? Because this R I've chosen to sum to 0, and so like the sum is going to be maintained on the when I add it to P. So that's fine.
It's obvious how to enforce the sum is 0, I guess.
So I'm not going to enforce it, right? So this is going to be a problem with the scheme. Yeah. So this is like I guess this is a first attempt, and it's not going to work. So the scheme is not sound, as you say, but it actually is zero knowledge, right? So the way that we show zero knowledge is the following. So we're going to choose, the simulator is going to choose a random Q, again of degree D, such that it sums to n over the k square. And then we can just write down like the sort of sum proof for Q. And this is going to be distributed exactly the same as the sum proof for P plus R, because P plus R is a random polynomial that sums to n on the square. Then the question is like, how do we simulate there's this other part of the proof, this R, right, that we need to simulate. But the way that we do that is whenever the malicious verifier queries the R part, we just answer it with Q minus P. And that takes one query to P for every query to the R part, and so that satisfies zero knowledge. Okay, so that's very nice. Unfortunately, it is not sound, right? Because as Abby pointed out, we don't have any guarantee that the proof is going to provide for us a polynomial that sums to 0 on this k by k square. Any questions about that? Okay, so this doesn't work. So here is how we might try to fix it, right?
If you just like check that with sumcheck.
Right. Yes, very good. Look, here we go.
Oh, okay.
So good. So what if I just like add another proof, right? That this polynomial R does actually sum to 0 on the on the square, right? Okay, so so I claim that this is complete and sound, but it's not zero knowledge. Anyone see why that is? Yeah.
You have to do the sum R thing, right? And then like R is P minus.
Yeah, exactly, right? So like
The same problem.
the problem is that, okay, so the verifier checks that indeed the sum of P plus R is n, the sum of R is 0, so we get like complete and soundness, but we don't get zero knowledge, right? Because I can just subtract off these two proofs, right? And like this sort of sigma function is like a linear function, right? And so sigma of P plus R and minus sigma of R is sigma of P, right? And so I have the same problem as I started. Okay, so here is kind of the magic. So the way that we're going to fix this is we're going to sum over the columns instead of the rows, right? So the sum over the columns is the same as the sum of the rows, so you might as well just sum of the columns instead. So we're going to have sigma P plus R on the right here, just as before, and then we're going to prove that the sum of R is 0 by summing over the transpose instead, right? Summing over the columns rather than the rows. Okay. So that's this is the like idea, basically the key idea as to why all of this works. So if we want to check it, then we just check the sum of the first proof and the sum of the second proof, and then we kind of do these consistency tests, right? So we need to sort of do a row consistency test and like a column consistency test. Okay, so it is complete and sound, and it might even be zero knowledge. So to analyze zero knowledge, I'm going to first make a simplification, right? Which is that I actually don't need to have two proofs here, really. I can just have one proof where I like add R and then I subtract the transpose of R. Because if I do this, that's like less information than this, right? And the soundness is unaffected because no matter what R is, like the sum of the R minus R transpose is always going to be 0. Right? So for any R, if I look at the summation, then I just get the sum of P. So now it doesn't matter, we don't need the other R sums to 0. This is going to be kind of complete and sound for any choice of R. And the way that we check it, again, we check the proof, and then we do this sort of consistency tests along the row, but then we also need to check sort of the corresponding part of R transpose. So we check on the column as well. So that just makes things a little bit easier to handle. Okay, any questions about this?
You didn't tell us what the simulator is doing yet.
Yeah, so we don't, so actually we don't know how to show that this is zero knowledge. We're going to need to modify it a little bit more, but this is kind of the main idea. So we do know how to show at least that, like, if you kind of focus on the k by k part, right, like the kind of this kind of combinatorial part of this problem rather than the algebraic part, then zero knowledge is not too hard to see. So what's the idea? So if you kind of look at what this R minus R transpose polynomial is, like restricted to this k by k square, it's basically just a random antisymmetric matrix. That's all you get there. And if you look at, so I'm going to call this R to be like, so this A, which is like R minus R transpose. And then if you look at any position in the proof, right, what does this tell you? It kind of tells you the sum over a row of this whole picture, right, like P plus A. Okay, so this by itself is definitely hiding, right? This is like doesn't tell you anything about P because this is just uniformly random in the field, right? So I can answer this question like if you just make this one query, I can say random gamma, right? And that's going to be correctly distributed. Of course, then the problem is, right? You don't just make one query; you can make a bunch of queries, and so we need to see, can the adversary kind of try to basically like remove this mask, right? Like remove this this part of the sum. And so intuitively, it's hard to do because in order to do this, you need to kind of get rid of all of these points, right? Okay, so this one is 0, right? But you need to kind of subtract off all of these. And there's k minus 1 of those, so you need to make k minus 1 queries to get rid of. Similarly, you don't have to do this, right? Because we know that the adversary knows that this matrix is antisymmetric, so he could kind of equally look at the column instead, right, and subtract off that. But that's also k minus 1 queries. Okay. So in both cases, we're okay because so long as we can keep track of the queries that he's making and kind of reason about them, like he's not going to learn anything about this polynomial P until he's made k queries, right? And then he learns like this whole row, but that's only k points, and so we can just query all of them. Right, once we've made k queries, once the adversary has made k queries, we have budget to query the entire row.
I'm not sure I got this. Can you say it again?
Yeah, sure. So the problem that we want to solve, right, is like the adversary has queried this position in the proof, right? And so this is like this sum, right? It's like the sum of everything in this row and the sum of everything in this row added together. And so long as like we have one of these kind of terms left over, then this is still going to like be a uniformly random, like it's going to look uniformly random because like we have something uniformly random that's like added to the sum.
Yes, you said focus on the combinatorial part. You're basically using that everything here is independent except the two things.
Exactly, yeah. So like the only constraint that we have here is that it's antisymmetric, right? Otherwise it's completely random. Everything is, yeah, exactly. Yeah, so this is explicitly not talking about the algebra, right? But like just the kind of those constraints. Does that make sense? Okay, great. Yeah, so you can do kind of a similar argument if you query multiple rows. You can kind of show that you end up with like a quadratic equation. You can show that basically you need to make k minus 1 queries, or you need to make at least k queries to learn like a row of P, or the sum of a row of P. Okay, so the simulation idea is basically we only query P when we know that we have to, like when the adversary has managed to like remove this mask, but we show that it's costly. Good. Everyone okay with the sort of the combinatorial part of this? Okay. All right. So now the algebraic part. So this is kind of where we get stuck. you know, now we have two kinds of structure going on here, right? We have like anti-symmetric structure, right? Because if I write this down, like R minus RT, like it's, you know, it's anti-symmetric as a polynomial as well, right? So we have like polynomial structure, like algebraic structure, and also this like anti-symmetry structure. You know, maybe some of you guys know how to reason about this. I don't. So you know, we basically throw up our hands at this point and say this is too much structure for us. Okay. So here's what we do instead. So for the soundness of the system, we don't need this anti-symmetric structure across the entire polynomial, right? We only need it to hold like in the sort of systematic part in this like k by k squared. And what we would like is that this, like the rest of the polynomial is like as random as possible in order to like try to simulate it as best we can. So, you know, I say random, it needs to be random, like subject to kind of the constraint of still being a low degree polynomial, right? So it needs to like agree as a low degree polynomial with the top left, but otherwise it's random. And so the way that we do this is basically by adding like the zero, like a random low degree extension of 0, right? So a random polynomial that's 0 on this k by k squared. The way that we do it is by appealing to this like combinatorial Milton-Satz. So what you do is you choose these like random polynomials tx and ty of the sort of necessary degrees, and then you multiply tx by the polynomial that vanishes on the set 1 up to k, and the same with y, with ty. And what the Milton-Satz tells you is that this is a uniformly random low degree extension of the function that is like 0. So it's a random polynomial that is 0 on k by k.
So previously, maybe the degree was k, now you make the degree a bit bigger.
Yeah, like 2k. Yeah, exactly. Good. Okay, so then what we get is that this A is a uniformly random low degree extension of some anti-symmetric matrix. Okay, and we know how to like kind of simulate like queries into the anti-symmetric matrix part, and then we rely on a work of Avi and Scott Aronson to show that you know, so long as this like the degree of this LDE is like 2k, for example, then you can actually simulate Q star queries to this whole A with Q star queries to the entries of the matrix M. Okay, so that's great. There is another part of this, which is like you have you know, the summation part. So like there is a part where you're like summing over the extension. I'm not going to talk about how we deal with that, but there is also a way to deal with that. Basically, some extension of this Aronson-Pinkston argument.
What is A and what is M and what are we simulating?
Good. So A is this, right? So I guess maybe I can show the structure of the proof and it'll be clearer. Okay, so A is a polynomial which is constructed from these parts, like this. So this is the proof, right? It's like R, T, and Y. Sorry, R, Tx, and Ty. The polynomial A is constructed in this way from R, Tx, and Ty, right? It's like R minus R transpose plus this like 0 polynomial that is given by bx times tx plus by times ty. And so A is the thing that we're summing over in the polynomial summation protocol.
I mean, A does not contain, A is like a mask or A contains P?
A is a mask, yeah. So we like A is just the random stuff, right? And then we like add A to P to get the thing that we sum of.
Okay.
And the sum of A, like the sum of the k by k square of A is 0, definitionally. So the thing that we need to simulate, right? We need to simulate like everything over here. So basically, you know, we can simulate the random stuff randomly. We just need to figure out like what the relationship is kind of between P plus A and everything else. So the problem is like when you query into this P plus A, right? Then you need to figure out, you know, what does the adversary know about you know, about R and T and like R, T, X, T, Y. And does that, like combining all of that together, does that allow me to like learn any information about P?
So have you shown us? I don't understand.
Good, yeah, so I guess, you know, putting this all together, right, what we
What
get,
is M in that next?
sorry, M is L minus LT, right? So M is like this like it's kind of the restriction of R minus RT to the K by K square. Yeah. Right, so this is like just, in particular, this is like some random antisymmetric measure.
So what do you lose the polynomial there in the?
So in this case, like in the Bivariate case, which you don't lose anything. Yeah, so this is actually like exactly Q star. Yeah, so the simulation is kind of, in the Bivariate case, is kind of perfect.
How are you going to simulate this Q star queries to A, just Q star queries to M?
So it turns out that like, I mean, it's so this is like a non-constructive, like this proof is like just shows that there exists a set. Like if I make a set of Q star queries to M, so to A, sorry, then there's a set of Q star queries to M that like I can make that will kind of allow me to like know what that distribution is.
Is this because you kind of have already like an explicit form of the interpolations? You have this like TX and TY polynomial. So
No, it's actually just because of the like, it's just a property of like random low degree extensions. So we don't need to worry about any of that structure. So like like basically what this shows is that like if I give you a low degree extension of a random low degree extension of a function f that is of high enough degree, then I can simulate access to that extension by making like the same number of queries to f as you do to the extension. Yeah. So like,
is it like obvious that?
no, I don't think so. I think there's some like lemmas in that paper that it's not like very hard, but it's yeah. Yeah, there's some is it's like linear algebra.
It seems like you would need for each query here to have a few.
Yeah, exactly. So the fact that it's really one is pretty surprising.
Yeah, but I wonder if you need it. Do you really need it since you're going to lose a polynomial factor later?
Oh, like do we need it to be that tight?
Do you need it to be tight in the two-dimensional?
No, not really, no.
Yeah.
Yeah, it just, yeah, I guess it is, which is nice. Yeah. Yeah, so it basically, you know, you could make those Q star queries to like just to this K by K bit, and then you would know exactly which points you need to query, right? But there's also like, if you make queries outside, then there is kind of there exists a set of queries inside that kind of explains the distribution that you see that is small. Yeah, I should say like this is not an algorithmic result. We like as part of this work also give like an algorithmic version of this where you can actually find out what that query set is. Okay, which we don't need for this, but we do need for some other stuff. Okay, so I guess like I don't know if people are convinced about the Bivariate case. It seemed like there was some mixed feelings. So I guess what I'm saying here is that like what we have ended up constructing is a proof where if you make, so firstly the sort of query complexity is maintained, so the honest verifier only needs to make like order of k queries to this part and order of k queries to here in order to check. And basically every query here you can simulate with one query to here. The claim that I make. So I don't have too much time left, so I'm gonna so I just want to talk about some of the things that come up in the multivariate case because I think they're very interesting. So the structure in the multivariate case is very similar to the structure of the proof is very similar to the bivariate case, right? So now you know, P is a cube, a hypercube, and all of these like R, T1, T2 up to Tm, these are all you know, polynomials in M variables. So we define this A in a similar way. I guess the one thing to note here is that this R transpose becomes like R, but with like the variables reversed. Right? It's cute, right? And then on the right here, this is just the generalization. This is the combinatorial Null-Sum-Satz for M variables. So that's the sort of the mask part, and then we have the proof part, which is this sumcheck proof for M variables, which kind of looks like a stack of kind of different sizes of proof for different numbers of variables. So I'm not going to sort of explain the innards of sumcheck, but we'll see a little bit like what information does this leak. So completeness and soundness are just the same as the bivariate case. So that's kind of, everything is kind of fine. Oh, I hadn't mentioned, but like there's some low degree testing going on here that I'm ignoring. So I'm just assuming that everything here is a polynomial. Okay, so what about zero knowledge? So, the adversary can now make queries to like this, this polynomial A, which is composed of some parts, and to this like sum of P plus A, which has like these many layers of subcheck. So the question is, when do we need to query P in order to answer queries to the proof? So if we kind of unpack what is going on in this like sumcheck proof, and again, like for simplicity, I'm going to restrict to just the sort of K to the M part, like the sort of systematic part. Then each of these queries corresponds to like a facet of this cube, right? So if I make some queries here, then I get like a couple of these facets, and then maybe I'll get some. If I make queries lower down, then I'll get sort of lower dimensional things. So each of these is what I call a subcube. So basically, it's like all the points. Like this consists of all the points in K to the N. Sorry, this should be M rather than N. So this is all the points in K to the M, which have like some prefix. So, and the length of the prefix, it depends on like how high up in this kind of tree you go. Okay, so we have like some collection, some like arrangement of these subcubes. And the important thing here is that if I make T queries to this sort of proof, then this gives me like T sums of subcubes. Right, that's like the information that I get. All right, so let's try to analyze this. So I'm going to define sort of the reversal of a set S to be like I take every point in S and I write it backwards. Okay. The observation here is that if A is an antisymmetric function in the sense that like it's equal, like A of x1 up to xm is equal to A of xm down to x1, then this sum, right, is identically 0 for all such A if and only if like this set S is equal to its reverse. Right, like
but it's not in this.
It's not in this case. Yeah, this is not an example. It's a non-example. But like if I want this to be identically 0, then I need S to be equal to its reverse. And this is the bad case, right? Because this is the case where like the adversary has made some set of queries and is able to kind of remove the mask. Right, we've made some set of queries that's identically like if I add them up, it's identically 0, and then the mask is gone, and I have to tell him something about P. Okay, so here is kind of the main combinatorial lemma. So what it says is that if S is the union of T disjoint subcubes, right, where this is kind of the formal version of that. But if you remember what a subcube is, you don't have to think about it. Then if S has this structure, then it is either really, really small or really, really big. Okay, like it is either like the size of this set, right, is either almost nothing, right? It's like almost T squared, or it is almost everything. It's like everything minus T squared. And the proof is kind of cute. So you basically you double count this set S as like S union is reverse and S intersection is reverse, which these should be the same if S and its reverse are the same, and that gives you like this kind of quadratic you can solve. And so this is actually where the polynomial blow up comes in, because notice that the size of S corresponds to like how many queries we have to make to the proof, right? When you make T queries, sorry, to the polynomial, when you make T queries to the proof, and we can only show that it's the most T squared.
What about the big case?
Sorry, yeah, so the big case you solve basically by, because it's a sum and you know the sum of everything, you can just subtract from the.
Well, this lemma should be, I don't know, maybe, I don't know if it's obvious or not, but can you say it again? You say if S is the union of some disjoint subcubes of any dimension.
Yeah.
Arbitrary dimension.
Yes.
If it's the same as its reverse, then regardless of dimension, it's quadratic.
Yes. I think it's intuitive. I guess the proof I don't think is obvious, but maybe it is if you like think about combinatorics a lot.
I just think about it, but it's, yeah.
Yeah.
Your definition of these subcubes, are you using the fact that the sum check is proceeding in a particular order?
Yes,
And
yeah, that's very important. Yeah, so the subcubes have to like it's like the prefix that I fix, right? So like this is not true if I allow like,
arbitrary.
if I think about arbitrary subcubes, right? So like the subcubes like are ones where I fix the first either.
And you would pick like a subcube and its.
Exactly, and then I could just So the point is that you can't do that. Yeah. Good. Okay. So that actually brings me to roughly the end, which is nice. So what we show in this paper is that NP has PCPs which are perfect zero knowledge up to sort of arbitrary query bound with polynomial proof length, constant query complexity, and where the zero knowledge is perfect. We also give a scaled up version of this result for next. So with exponential proof length, constant query complexity, exponential query bound, because you can just absorb that into the exponential proof length, and so actually that means that you don't need to really give a bound for the number of queries, and perfect zero knowledge. So in the sort of classical PCP world, like next is easier than NP, right? Like the scaling up is easier than scaling down. Here, this is not really true because our simulator is still polynomial time, right? So it doesn't have time to like write down even a simulated proof. Like it can't like reason about like explicitly about large like objects that are the size of this proof. And so we need to come up with ways to like implicitly reason about these like large polynomials and like sumcheck proofs and things like that. So this leads to like a bunch of really interesting algorithmic problems that we have to solve, which I would be happy to talk about offline. Okay, so future directions. I think one that's really interesting is that this proof length is some polynomial in Q star. I don't know, it's like Q star to the 4 or something, like it's something, it's not huge, but it's a lot bigger than Q star. The lower bound is that Q star is equal to L, right? So like how close can we get these things, right? Can we really get down to like linear in L? And then there's some interesting connections to like quantum PCPs and quantum codes. So there is a paper with Siki on it, I believe, that shows that sort of the zero knowledge property of code, which is related to the zero knowledge property of PCPs, transfers, like it becomes like a dual distance property if you look at it algebraically. And this is the same property that you need for like good quantum codes. It's kind of this like CSS property. And so, maybe there are some interesting connections there to quantum PCPs. Like zero knowledge PCPs seem to be kind of close to quantum PCPs in some way. And that is it. Thank you very much.
Does this say anything about the interactive proof protocol, some zero knowledge property when you do it for the permanence? Can you do any statistical or perfect zero knowledge?
I don't think, not that I am aware. Yeah. I don't really know of any applications of this stuff to like interactive proofs or anything like that.
You need the proof string.
Yeah, like the proof string and like the kind of zero knowledge we have, right? In interactive proofs, like you have like a rewinding simulator, right? And here we have like, we're relying on something else, right? We're relying on this like being able to generate the proof adaptively. So I don't know of any connection. Would be interesting.
Okay.
Thank you.